Hi, my name is Srinivas Narayana, and today I'm going to talk about my research project, which is about optimizing traffic management for online services. We are surrounded by large-scale online services which appear to be always online for millions of users. Some examples include search, like Google, or shopping websites like Amazon, or social networking websites like Facebook and Twitter. For these services, performance is crucial for revenue as it directly impacts customer retention and the click-through rates for advertisements. However, users have decreasing tolerance for bad performance, and experiments have shown that even a few hundred millisecond increments in page loading time can have a bad impact on user experience. But performance is not the only thing. The operational costs for running these services can also be significant. So these costs include the server power, the bandwidth costs that are required to connect the service locations to the internet, and also the management costs which are running through the lifetime of the service. So let's talk a little bit about a simplified picture of an online service, which is fairly representative of a large number of services. So I'll represent the internet here as a cloud to which users connect through their local ISP. And the online service itself runs out of multiple geographically distributed data centers, each of which is connected typically to the internet through multiple ISPs. And the users usually reach the service through a front-end box which makes the choice of which service location they go to. And this choice is the first step, is one of the key decisions that goes into the traffic management for these services, and we call this choice as mapping. So once the request reaches the data center, the egress at the egress of that data center, the response is then routed along one of many paths back from the data center to the user. And typically this choice is just restricted to the first hop, the ISP that is chosen to send the response back. And we call this choice as routing. So mapping and routing together determine the forward and the backward path that the service administrators themselves can control. And together they determine the amount of control that the service has over the wide area paths that requests and responses traverse for the service. And so they are quite important for the performance and costs in general. So let me talk a little bit about the specific question I'm investigating. So today mapping and routing work independently. So there are good reasons for this. So these two systems are themselves large and distributed, and so it's a good idea to keep them separate and modularize their administration. But there's also another reason. Mapping and routing have typically slightly different goals. So the mapping system tries to optimize for the latency and the distribution of the request load among the service locations, the data centers, whereas the routing system tries to optimize the ISP costs and also maintain the link utilization at a manageable level, and of course offer good path latencies to the responses that they serve. And today, coordination between these two systems is often manual and slow. The question that we're asking is, can coordination help? So we show that in this work, in principle, we show that coordination can impact latencies and bandwidth costs pretty significantly. So if mapping and routing have incompatible objectives, the service can end up in a situation where it neither has the best cost nor the best performance in terms of latency. But not sharing relevant information between the two systems can also be bad. In particular, link information is pretty important for the mapping system to make better decisions. We use an optimization framework to model the interaction between these two systems and show that it's actually possible for mapping and routing to exchange the right information and coordinate the computations so that they can actually converge to an optimal point achievable by a joint system. With some workloads from an operational content distribution network, we show that in practice the benefits depend on the service, and quantify how by using some latency and cost variation patterns. If you need any extra information, feel free to get in touch with me at narayana@cs.princeton.edu. Bye-bye.